number was 13.
13.
Mm, 59 as well. 51.
Alright, so 13. We've got 2 sine squared plus 1 equals 3 sine x. So Sarah, what did you try?
Well, I tried figuring out what to do with that sine squared. I
Mm.
can never really remember what any of the rules are, and whenever I did, it either broke mathematical rules or just didn't fit.
Algebra. I'm trying to solve 2a squared plus 1 equals 3a. What do you do? Huh?
Minus 3a.
Bring the 3 over, set it equal to 0, and factor. Okay, so the reason why we need to do it in that method is because we have both a squared and a involved in the equation. If we simply had just the a squared, then we can get a squared isolated and square root both sides. For the same reason, we have sine squared and sine. So what we need to do is we need to get this puppy set equal to 0 and factor. So if we write 2 sine squared, bring that 3 sine x to the other side by subtraction and write it in the decreasing order of exponent. Now we're just going to factor. When your leading coefficient is prime, I only have one choice, 2 and 1, and your constant is prime as well. It's not so bad to just go for the factoring. There are methods where you multiply 2 times 1 and split the middle term. But if you just, do your, I guess you could call it guess and check. The only thing you've got to be careful of is because we have this coefficient up front, you cannot just say to yourself, what multiplies to be 1 and adds to be 3, because there's 2 factors into that whole process. So we could say, well, 2 sine squared is 2 sine x sine x. And if you're like, I really do not like trying to factor that with the trig function in there, we could just transition through a substitution process, call that sine x, and let it be a. And anytime your substitution is going to be helpful for you, you're always going to take that linear variable, the sine x, and call that your variable. Okay, so you could do the same thing over here. You say, oh, 2a squared, that means I need a 2a, and I need an a. And then pretty much if I've got a 1 on the back end, I have no choice. I better have 1 times 1 is 1. So now we are gonna, you might have, I believe you have a quadratic in your homework that doesn't factor. So if it doesn't factor, you have to use the formula. I'm pretty sure this one does. Okay, so here we do get a 1a and we get a 2a. Conveniently, they both have to be the same sign. They both need to be minus. And if they're both minus, then I sure will get a positive 1 for the constant term and a minus 3a for the linear term. So they're both minus here. Okay. So either way you do it, it's totally fine. Once we get it factored, what do? Set them both equal to 0. So if you're okay with factoring like this, you've got 2 sine x minus 1 equals 0, or sine x, minus 1 equals 0, in which case you get, move the 1 to the other side and it's positive, and divide by 2, you get sine x equals 1/2. or sine x equals 0, excuse me, sine x equals 1, whoops, don't lose your x. Over here, if we say 2a minus 1 equals 0 and a minus 1 equals 0, we get a is 1/2, a is 1. If you're going to go the substitution route, just be careful in that you are not done. If this was an algebra class and your original problem was this black problem, yes, you'd be done. But you created a substitution by letting a be sine x, in which case now I have sine x is 1/2 and sine x is 1, which is what we've got basically over there. So either way you do it, if you really don't want to try to factor with the trig functions there, then do a substitution. Otherwise, we're going to get this. So now we're going to say to ourselves, we're going to draw. Okay? Even if we're not going to draw, even if this is not special, then we still need to consider all areas in one revolution of the angles from 0 to 2 pi, which is one revolution of the circle. Where is sine positive? So sine is positive in the first and the second. And if we label our triangle with respect to y over r, so remember our sine ratio is y over r, we can complete the triangle. You either do Pythagorean theorem or you recognize this is going to be the square root of 3, which means that this is 30 degrees. Twofold, it tells us our domain that we're giving our answers is, as well as the fact that we're giving our answers in radians. So that's pi over 6. That means this reference angle is also pi over 6, and the rotation is stopping pi over 6 units short of pi, which again is 6 pi over 6. The more you can think in radians, the better off you're going to be. Rather than having to take 150 and convert it, you can absolutely do that if you want. But if I'm stopping short of 6 pi over 6 by a unit of pi over 6, then that is 5 pi over 6. Okay, that solves the first equation. Here, make your ratio. This is y over r. And hopefully, if you try to draw in the same manner, and you say, you're like, wait a minute, what kind of triangle is that? And you do this a few times, and then you probably will start to recognize that if sine is 1 or -1 or 0, it's one of our quadrantal angles. Okay, so you could even do x squared plus y squared equals r squared, and you confirm that x is 0. So we're up here at 90 degrees. Or if you like the defunct triangle kind of method, if my hypotenuse is 1 and this side lengthens 1, that means there's no room left for this. It kind of folds flat. Don't fold it down, fold it up against the y-axis. It gives us this pi over 2 radian measure. So we got pi over 2. So that's number 13. 59. Does anybody have any questions on that one? All right. What?
When I did it, I got the values in the book, but flipped over the x-axis.
Negative
Yeah.
instead of positive?
Yeah.
Wait a minute, you're solving for angles. So,
Well,
what?
I just mean that I got the same angles except flipped upside down.
Oh, you got them in the wrong quadrant.
Yes.
Okay, so, does anybody need to see, so here, let's see, 59, the original equation is cosine squared x minus 3 sine x plus 2 sine squared x equals 0. I did mention before we left on Friday, although you might have missed it, I'm not sure. Okay, if I compare equation 59 with equation 13, 13 is real sweet because of a specific reason that's not so sweet with 59. What's going on?
Well, it's all signs there, and there's a cosine
We got all one trig function, we got a squared one, we have a linear one. I'm not bothered by that because it could be it's called quadratic in form. We can factor it like a quadratic or solve it like a quadratic with a quadratic formula. The fact that that has both sine squared and sine is kind of sweet, but this cosine is kind of screwing up the mess. Now, if it had the same two coefficient, 2 cosine squared plus 2 sine squared, we can like factor out the 2 and make it 1, because sine squared plus cosine squared is 1, but that's not happening. So, what do we have to do? The Pythagorean theorem. We're going to substitute so that we get all the same trig function, and this guy kind of pretty much determines which trig function you're going to use. We want all sines, because our linear term is sine. So we're going to substitute for cosine squared. So cosine squared is 1 minus sine squared. It's already set equal to 0. So 2 sine squared and a minus sine squared is a positive 1 sine squared minus 3 sine x. This is the one that you need the quadratic formula. Did you do the quadratic, Justin? Oh, you tried to factor?
Well, when I transcribed it into my notes, I forgot the 2. That was the problem.
Oh, you made the whole problem a whole lot easier.
Yeah. But
Okay.
then it still didn't work.
So, let's just talk about this. I'm just gonna cheat for a little minute because, well, okay. Does everybody understand? Well, here, let's just talk about it. Ax squared plus bx plus c equals 0. General form of a quadratic equation. So the quadratic formula is what? X equals minus b plus or minus. Everybody knows this quadratic formula, right? Math is not about memorizing formulas except the quadratic formula. So it's x equals. So how is it impacted by our trigonometric quadratic and form equation? It's no longer x equals, it's sine x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. You must split it up into 2 equations. All right. So take care of this. You got your calculator. You're going to have your scientific calculator on your test. Square 3 plus the square root of 5 over 2. So you punch that up. 3 plus the square root of 5. Oh, make sure you put parentheses around it or hit equals before you divide by 2, because otherwise you won't get the right decimal. 2.618, blah, 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 blah. Do not round in the middle of the problem. Sine x equals 2.618, blah, 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 blah. Okay, you may not chop decimals off at this point in time. However, if we thought about this, and we say, oh, I need to make myself a fraction because I need y over r. And if we thought about, obviously it's not going to be a special ratio, but if we think about this for just a second so that nobody gets confused, how can the side length of a leg of a triangle be 2 and the hypotenuse be 1?
Can't.
It can't. sine function. The sine function varies between positive 1 and negative 1. So all of my sine ratios are decimals or fractions between 1 and negative 1. That right there is another reason why this is busted. If you do, now, it's kind of nice to go ahead and say the inverse sine of 2.618 blah, 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 blah. You would make use of your answer button, A and S key on your scientific calculator, which sometimes is its own button, or it could be the second function of your plus minus button. It could be involved in your mode, text, whatever thing, I don't know. But do not tell me on the test, this calculator the testing center gave me doesn't work. Because this is a bogus thing. Guess what your calculator is going to give you?
An error.
Error. It's not the calculator, it's your brain not thinking completely fully enough about the problem. Okay, so I don't want that. Get yourself a scientific calculator that you can practice with between now and the test. Okay? If you use your graphing calculator, honestly, it's going to give you the same thing. So if you use your cell phone, it's probably going to give you the same thing. I don't really know. So be careful about that. This is bogus. It's not going to give me an answer to the equation, but I still have that other one left that we still have to deal with. What time is it? I'm going to actually leave this for you guys to do. I don't think that that's going to be a thing greater than 1 or less than negative 1. 3 minus the square root of 5 divided by 2. So, oh, it's 1.5. Oh, whoops, it doesn't help if you don't type 5. 3 minus the square root of 5 divided, whoops, over here, delete that, divided by 2. Yeah. So you're going to get some decimal, 0.381, blah, 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 blah. And that has 2 answers. The calculator will give you the first quadrant 1. You got to work for the second quadrant 1. Sine ratio is positive in 2 spots. Okay, 59 is probably in the section where they want you to give it in degrees. Is this one of the problems I told you to do it in radians? It totally is. So to get the radian measure answer, you just want to go to your half sheet of blue paper, which probably you just, well, I guess there were some even problems before that. All right, real quick, what's up with 51? Oh, this is fabulous. Let's talk about 51. And then I'm going to throw you to the wolves with it. I think we're solving between 0 and 360. So you're solving in degrees. What rotation around? All the angle measures that are going to make that true. What's the problem?
Sine, cosine.
I got both sine and cosine. It is a dilemma. All right. We were able to get one trig function in problem number 59 because we did a trigonometric substitution using the Pythagorean identity. But that's only if we have squared trig functions, sine squared, cosine squared, which I don't. Total bummer. We could think about turning it into tangent, but the fact that there's a 1 there kind of makes that method a little bit of a pain in the butt. Actually, it probably doesn't even really work. Okay, so I really love those to be squared. Can I just square everything? No, I cannot just square everything. The Pythagorean theorem says a squared plus b squared equals c squared. 3 squared plus 4 squared is equal to 5 squared, but does a plus b equal c? Does 3 plus 4 equal 5? No, you may not square individual pieces of an equation independently of themselves. I can square sides, absolutely. Okay, so we're going to square both sides. Now, you have a choice. I personally would like to have a trig function on one side, a trig function on the other side, square both sides. You can square both sides the way it's written. You are going to get a middle term of sine x, cosine x, and I'm thinking we should probably avoid that. So, is it okay if we just bring cosine to the other side?
Yeah.
Alright, so let's scooch in. Because if you really want to do it the hard way, just square it like it is, but I recommend not. Now, we are going to square the side, and we're going to be super careful about the fact that I'm going to FOIL over here because it's a sum. But how do I square 2 sine x? I say 2 sine x times 2 sine x, and it's all multiplication. We square the 2, we square the sine x. It's like AB quantity squared, A squared, B squared. So be careful. There is no plus sign here. It is not a FOIL problem. We're just going to get 4 sine squared. What? I got 1 plus 2 cosine squared. No, excuse me, hold on. 2 cosine x plus cosine squared. Okay, similar to 59. Let's just talk about it and then you can finish it on your own. Okay, well here, let's just make it less step looking. I have an equation. I've got trig functions on both sides. That doesn't bother me right now. I do have cosine squared and sine squared. That has to be fixed. I only want one of them, but which one do I want to keep? I want to keep the cosine squared because
You have more cosine.
my cosine right there. So we're going to substitute. So this is going to be 4 times 1 minus cosine squared. And you do a bunch of work and you get a bunch of answers. All right. So the remaining equations that we still need to deal with from this section are problems where we are going to solve for all angles. Radians. Ooh, let's do one like that. Here, let's do this one. This happens to be number 68 on page 279 if you like. I don't know. Doesn't matter. Cosine of 2x minus pi over 4 is equal to minus root 2 over 2. Okay, we want to make life easy on ourselves, not more complicated. You just had a test on the cosine of alpha minus beta. There's a formula for it. That formula makes this side a lot more complicated, doesn't it? Let's not do that. In fact, how much do you love this expression, 2x minus pi over 4? How about we call it something like A, B, anything but X? What do you want to call it? I don't care.
U.
Huh? Oh, you like U. All right. U is 2x minus pi over 4. Because once you do that, you're like, should you think you'd be doing with this negative root 2 over 2?
Drawing a triangle.
We could draw a triangle, or we might want to make it our basic ratio. This is the rationalized form of 1 over root 2, which we could actually get if we multiplied top and bottom by root 2. I get minus 2 over 2 root 2, which is minus 1 over root 2. Okay, so root 2 over, most of the time you get this and you have to go that way. Well, now we could draw our triangle just like Justin recommended. Cosine is negative in the second and third. But if we label it, it looks weird. In fact, the 2 on the hypotenuse, you might want to call this, I don't even know what you'd call it. You might call it a 1 because the radical's already here. Okay? But if we instead label it with this, so now x over r is negative 1 root 2. You're like, oh yes, 1 root 2. All right? So radians. This is 45 degrees, which is what kind of radian? Pi over 4. The angle U is that black one, which, whoops, this is pi. If we want to give pi a denominator of 4 so we can think, that's 4 pi over 4. So if we stop short pi over 4 from 4 pi over 4, is everybody good that we're at 3 pi over 4? Yes?
Yes.
What else?
Half that over 4.
Pi over 4 units past 4 pi over 4, so U is 5 pi over 4. What's the problem? We got 2 problems. I was supposed to solve for
U.
We solved for U. I really need to solve for
Cosine.
X. What'd you say?
The cosine of U?
We did. The cosine of U is negative 1 over root 2. We drew our triangle. We labeled it with the cosine stipulation. We finished it. We figured out our angle, and we figured out our angles. So this green equation, cosine U equals negative 1 over root 2, is solved right there. Okay, we want to solve for x, but before we do that, because this is what we're going to do to solve for x, we want to solve for all angles. All of them. There's 2 of them. How many more are there?
2
An
more?
infinite number of them. What do they look like if I was going to draw rotations? All the way around, then stop there. I could go backwards and stop there. I could go all the way around and stop here. Okay? All of them are multiple revolutions of this. Okay? So we are going to add 2 pi k, where k is an integer, so this right here is going to account for multiple revolutions. Multiple revolutions, which is going to produce all solutions.
And how'd you come up with 2 pi r?
So I want to go, here, there's too many circles over there.
Oh, k is revolutions.
K is revolutions.
Okay.
So if I go once around, that's 2 pi, plus I want to end up there, so I'm going to add the 3 pi over 4. So that would be where k is 1. Okay? K is going to be an integer. Well, let me write that in black so it doesn't get lost in my little blue diagram here. K is an integer. That allows us not to have to say plus or minus, because we can go backwards, but if k was negative, I would go negative 2 pi over 4 is actually, if you do the math right, you're going to end up there. Okay, so I went all the way around negative, but we're adding, and we just go right here. So you can do plus or minus 2 pi k, but most of the time we write this. Now, how important do you think this wording is? William says it's very important. It is. Otherwise, I probably wouldn't ask about it or point it out. Most of the time, variables in math represent real numbers. Any real number. Okay? We don't want any real number. We want specific revolutions of once around, twice around, 3 times around. Go backwards 3 times and then get to this angle. Okay? So, we really want to specify that k is an integer. Okay, so we've got that for that angle, we've got this for this angle. Whoops. I think most of the time it's 2k pi. 2k pi, 2 pi k sounds really weird. Okay. Now, I have to, it's very important that you do this before you convert back to x. Do before converting to x. Because this picture is the picture of the angles that are going to solve this equation. Okay, so now we just have to take these 2 u equations and go backwards with respect to the red equation over there. U is equal to 2x minus pi over 4. Okay, so I think it's probably easier to solve this for x and then impact it with this, rather than taking these expressions, plugging it into u, and solving for x. So would you agree? So let's just solve for x first. Okay, so I'm going to bring my pi over 4 to the other side. I really don't want to divide by 2. If I divide by 2, I'm going to end up with this. How much do you like looking at that? Do you think I want to see that as an answer on your test? Do you think your calculus teacher is going to want to see this? I didn't do my job if I let you do this. Ugly. How else can I get x by itself besides dividing by 2 to create this wonderfulness? We can multiply by 1/2. So the sooner you get comfortable with, I don't want to create this big ugly fraction. So rather than thinking divide by 2, how about we just multiply by 1/2? I did my job. All right, so what do I get? If we want, we're going to say 1/2 u plus pi over 8 is equal to x. Okay, so now all we have to do, I'm just going to flip-flop sides. X equals 1/2 u plus pi over 8. Okay, well now what we're going to do is we're going to take individually, we have to do it individually, plug that u in, and then we're going to take the other one and plug it in. So what do I get? 1/2 of 3 pi over 4 plus 2k pi, don't forget the plus 1/8. Whoops, pi over 8, not 1/8. So what do we get? 1/2 times 3 pi over 4 is 3 pi over 8. One half times 2k pi over 2, I get k pi plus pi over 8. Oh hey, look, 3 pi over 8, pi over 8. You think we probably should add that. We get 4 pi over 8. What's 4 pi over 8? Pi over 2. Finally! That's one of our answers. Guess what we have to do now? do the same exact thing for that. Let's just finish it up so you have it in your notes. So now we're gonna say x equals 1/2 of 5 pi over 4 plus 2k pi. Don't forget the plus 1/8, or excuse me, I keep saying that. Pi over 8. Would you agree this is a lot simpler than this mess up here? So let's just do the arithmetic. We're going to distribute the 1/2, so we get 5 pi over 8. Put a 1 underneath that so we can visualize how our 2's are going to cancel. So when I distribute to the other one, 2 is going to cancel. I've got k pi. Those two create 6 pi over 8, which reduces by 2 to create 3 pi over 4 plus k pi. And you have just expressed all of the angles for that cosine. Oh, dang it. All right, we didn't get to do 4.1. We'll just have to squeeze it all from that. Okay. Some of your answers, or some of your equations, will be that. We could square both sides. We get sine squared and cosine squared. We could then convert with a Pythagorean relationship. Huh?
Is it multiplication? Can't we just substitute?
Substitute what?
I cannot remember. That's okay.
2 sine x cosine x, those formulas is the sine of 2x. And now guess what this is? A super easy problem than that. Like our substitution. Now, I want to get this straight because it didn't really come up over there. I cannot divide by 2. The order of operations when I plug a value in is I take my angle, I multiply by 2, I take the sine of that angle. The reverse order of operations is not going to produce the same answer. I cannot take the sine of my original angle, get that ratio, multiply it by 2, and get the same answer. So you may not divide by 2. I'm just going to leave this. We're going to call this our u. We're going to solve this easy equation that you're totally excited about because you haven't gotten easy ones like that for about 65 hours. And then we're going to convert back. Okay? Let's see. The only problem with this is we need more answers. So if they said solve between 0 and 2 pi, because, oh, whoops, this is not supposed to be x, this is u. Because when we go back to u, or back to x, if I divide by 2, u over 2 is equal to x. If I solve this from 0 to 2 pi, you're going to say, well, I need my first quadrant angle, my second quadrant angle. Okay, 1, 2, root 3, let's just solve it at 360, because that's easier. 30, 30, u equals 30, 150. To convert back to x, we divide by 2, so my x angles are divide by 2, divide by 2. My original equation said solve between 0 and 360. Doesn't the sign, if I thought about this graph, it compresses it. It does 2 cycles of the function by 360. So we need actually more answers. And you can do it in general and then plug in values for k. Or you can just say to yourself, well, what if I went all the way around and said, well, what is that angle? If I do 360 plus 30 is 390. If I cut that in half, am I still within the domain of the original equation? 390 divided by 2 is 195, I think. Double check that. Yeah, it is. Okay? So, totally in the domain. Okay? I want to do the same exact thing for this angle. I'm going to take my 150 and add 360. Okay, so if I add 360 to 150, I get 510. If I cut that in half, I get 260. No, 255. Still good. Can I go more? Can I go around again? So if you notice here, we added 360. We added 360. We add 360 to the U angle, the picture, not the X ones. If I go and take my 390 and add 360, I get what, 750? And if I cut 750 in half, I get 375. And that's too big. Okay? So anyway, sorry I kept you over by 4 minutes. I should have not solved more equations for 4 minutes. All right.
We're gonna need to